Hey, okay, well, welcome back here. This is, as I mentioned, day number 8. This is the second lecture of day number 8, so we just took our 20-minute break here, and let me just say it again. Well, we're about to shift gears here. Well, we just got done with 8 chapters, and particularly that last one, chapter 8, was a long one. So work hard on that one. I think you guys will have a lot of questions for me on that one, and so keep the questions coming, and I'll keep the answers flowing back. Hopefully that is communicating well with you. As I said before, this whole distance learning, we're learning it together here, and so I hope this is working well. And I'll say it again that when I head home tonight, I will start grading those tests and finish them up tomorrow, so you can see your scores by probably Thursday afternoon, or maybe even by lunchtime. That might be a little early, but somewhere in there I'll get all that stuff done. So let's turn the page here. I brought out some new equipment because we're about to jump over to chapter 11, and so I'll call this the second half of the class. It might be a little more than half, but when we finish up here today, we're actually halfway done with summer school. We're completing week number 3 here, and so we'll pick up again on Monday with the start of week number 4. But for the next 4 chapters, and so we'll start here at chapter 11, we're doing the structure of matter. By the way, I did skip over those other 2 chapters, 9 and 10. They're really good chapters. And so those of you who might have extra time, let me encourage you to read through that for your own education. I won't test you on it. We're just not going to have enough time to cover all that. And it's time to move past all that mechanics stuff and start talking about some other parts of physics. And so, as I said, chapter 11 is the start of what they call the structure of matter. And the next 4 chapters in the book, although we're scheduled to do 3 of those 4, so 11, 12, and 13 all fit together. We will never spend 8 chapters on one idea again, like we just did with mechanics. Like I said, we disproportionately do the mechanics. And the structure of matter is really a big 2 parts. We start off with this kind of idea: is what is the structure of an atom? What does an atom look like? And for that matter, just what is an atom? And what is a molecule? And what is an element? What is a compound? And so we've got a lot of definitions here at the beginning. And so the first half of this chapter, well, maybe a third, the first third of this chapter is a little booky, if you will, a little dry. It's just a lot of facts and figures here. But let me talk about the structure of an atom. And maybe the best place to begin is to talk about a helium atom. The scientific symbol for helium is He. In fact, let me draw your attention over to this giant periodic table over here. And of course, if we were in a face-to-face setting, you would be able to see this giant periodic table. But if you have never seen or heard of the periodic table, let me take a moment to introduce this to you. The things that are laid out here are laid out in a really useful pattern. The shape, the structure, the symbols, the numbers, all of this has a lot of information. And so there's a lot of power here in this periodic table. And so as we talk about the structure of matter, we're going to come over here a lot and kind of get some numbers. We're going to see where it is. We're going to see, are they to the left or to the right? Are they in the middle band here? Or are they the lower band here? Are they above or below this dotted line? Or we'll look at these red numbers. We'll look at the black numbers. We'll look at the symbols. All of these have a lot of pieces, and we won't be able to talk about all of it, but I do want to point out that you need to start to get familiar with the periodic table if you're not already somewhat familiar. And that's why, let me grab the book. Now, of course, you have the PDF version of the book. But when you launch that PDF version of the book, the first thing you see is the inside front flap of the book. And that's a periodic table. And so there is your periodic table. And then this is even color-coded a little better than that to add. They've got the green, the yellow, and the light orange and dark orange and the light blue and the violet. And so all of these different places, these shapes, have a lot of information in them. And like I said, let's learn a little bit about that here in this chapter. And so helium is a good place to start. Let me come back over here to the periodic table. In case you don't know where it is, actually let me get a pointer because it's a little too high for me to point at. Let me grab this meter stick and come over here. But helium is right over here in the top right of the periodic table. Notice there's a red number 2 up here, and then down below there's a 4, just a little more than 4. It's 4.003. I want to talk about those numbers, but I'll start with just the symbol He. That's telling me that's helium. And of course, if you follow along, coming way back at the beginning, at the top left, it says number 1, and as you go across, number 2. And I'm looking at these big red numbers, number 3, number 4, and then it goes all the way across, number 5, number 6, number 7. And so reading those numbers across is one of the part I want to explain. And I want you to kind of get out of this discussion, and so this is why I call it the structure of an atom. What does an atom look like? Because all the atoms are listed in this periodic table, and all these atoms have roughly the same structure, the same shape. Now, are there differences? Oh, absolutely. And so I want to give you the big picture, but then I also want to talk about the individual pieces, things like what makes gold different from aluminum, or helium different from hydrogen. And so those are all real important discussions to have. But I'm going to start with the bigger picture that they all look the same. I guess a good analogy is, and I usually say this, as I look around the room with face-to-face students, I could roughly describe what a student looks like, or what a human looks like. And all of you in here have that same basic structure. Of course, you also have different subtleties. For example, I would say all of you have 2 arms. All of you have 2 eyes. All of you have 1 nose. You have 1 mouth. All of you have 2 ears. You get the idea, 2 feet. And inside you have 1 heart and 1 stomach and 2 kidneys. Now, I know there's some exceptions with accidents and surgeries and birth defects, but in general, that is a good way to describe any human. It doesn't matter whether it's male or female, old or young, or what the ethnic group is. That describes humans kind of in a general picture. And I want to say, that's what I'm going to do here. I can describe the structure of all these atoms about the same, but each one is also different from the others. And so, just like students, I would say, some of us don't have hair, and most of you guys out there do have hair. And so there's differences from one human to another, but there's also this general similarities between them, and that's what I want you to be able to see here. And so helium is a good one to start with, because it is not the simplest one. As you'll see, hydrogen is the simplest one. But hydrogen is so simple that you don't see enough structure to get the picture. So I'm going to go to helium, which is the next complicated one. I'll call it the second simplest one, but it's got enough structure to it. And here's how I would describe helium. Helium, first of all, as you already saw, would be labeled He for helium. So coming over to the periodic table, that's the first thing I see here is He. So there's helium. And so there's like neon, there's fluorine, there's oxygen, there's nitrogen, there's carbon, there's boron. But I'm also going to look at the number in the upper right-hand corner. The number in the upper right-hand corner, which in this case is number 2. But as you scan across, you can see that every number is a little bit bigger, but every one has a number. See, what that number represents is the number of little tiny things called protons that are in the center of the atom. In my case, I will draw it on the board with a little circle and I'll color it in. And I'll just kind of point to it and call these then the protons. And the reason I drew two of them is because there are two protons in the center part, which we will call the nucleus of an atom. So, coming back to this periodic table and scanning across, you can see that every atom, here's boron, carbon, nitrogen, oxygen, fluorine, neon, they all have a number in the upper right-hand corner, but it is a difference number. And so this is a way of me to say that all atoms have a overall general structure of a certain number of protons. But what makes each one different is the number of protons. And so starting at the beginning of this periodic table with hydrogen, hydrogen has a number 1, and what that means is it has 1 proton. Whereas helium, which I'm trying to draw there, has 2 protons. Lithium has 3 protons. Beryllium has 4 protons. Boron has 5. Carbon has 6. And you get the idea. And we can come all the way across here, and getting up to the big ones like uranium has 92 protons. And so again, I hope what you get out of this is every atom has a nucleus. Every atom has protons in that nucleus. What makes gold different from aluminum is the number of protons. In fact, maybe since I just said aluminum and gold, I'll come over here and point it out. So here's aluminum, and if I look at aluminum, the number is 13, whereas gold, which uses the Latin, so it's Au, is 79 protons. And so the lesson here being that in the center part, which we'll call a nucleus, every atom has protons. And we just need to look at that periodic table and say, well, how many protons does it have? I don't know if this is helpful or not. My drawing might be the same, but I thought I would bring some colored blocks up here and say, okay, if I am going to then build my atoms, and so this is the building blocks of nature, so maybe you'll pretend I'm a God's elf here, and I'm going to build an atom. And said, let's build nature, and so let's make helium. I would look at this chart and say, oh, helium needs 2 protons. And so if I let the blue ones represent protons, I would grab 2 of them out of this construction box. All right, so there's my 2 protons. Now, interesting enough, those are not the only things in the nucleus. It turns out that there are 2 things in the nucleus. The second pieces in the nucleus are called neutrons. By the way, the name comes from the early scientists discovering that these things that I'm representing in blue out here or coloring in on my board, these protons have then a positive electrical charge. And so I'll just say that the protons have a charge, they're positive. We won't do too much with that yet until we get into electricity and magnetism here, but this is where electricity and charges come from. They come from, at least one source is the protons. We'll see the same thing with the electrons. But the neutrons are, of course, called that because they have no charge. They're not positive charged, they're not negative charged. It's why they were the last part of the structure in the atom to be discovered, because nobody knew they were there. They just didn't interact with any of the equipment that scientists were using at the time. And in fact, we can group these two together and give it a name which we call nucleons. And the nucleons is really just kind of an overarching name that says what's in the nucleus. Okay? And so protons and neutrons are in the nucleus. And so collectively, these four items are in the nucleus. And so I'll call it the inside piece. It's way at the center. And so here is the nucleus. So I'll say it again. The nucleus is the center of the atom. Anything in the nucleus is called the nucleons. And it turns out there are two things inside of there, protons and neutrons. Now, you'll notice that I put 2 neutrons here, but how did I know that? Well, let's come back to the periodic table. As I come back over here to this periodic table and I look at helium, helium is right here, and down to the right, but at the bottom, there's a number 4. Now, it's 4.003. So it is a little bit more than 4. But the closest integer is 4. Let me just round it for the moment to exactly 4. We'll talk about the little extra in just a second. But if you round it to the nearest integer, then that number is telling you the number of nucleons. It's not telling you the number of neutrons. Did you catch that difference? It's the number of nucleons. There's 4. So that's how I knew there should be 2 neutrons, because the number 2 in the upper right-hand corner tells me the number of protons. The number 4 in the bottom right-hand corner tells me the total number of nucleons. So if I subtract those two, 4 minus 2 leaves me with 2. That's how I knew there would be 2 nucleons. This is a long way of saying there is no number in this periodic table that directly says how many neutrons. The two numbers tell you, number 1, how many protons, and then number 2, how many total nucleons do you have. And then there's no point in writing down the number of neutrons, because you could just subtract the 2. All right, so looking at that, I have now begun to make my nucleus. And for whatever reason, I like to use the orange blocks to represent my neutrons. So let me grab 2 neutrons and put it in my nucleus. Now, for reasons we're not going to get to in this chapter, the neutrons would prefer to kind of intermix with the protons. So let me make more of a checkered board pattern for the protons and the neutrons. And so that's what I did in my drawing, and that's what I'll do with my blocks. And I would say, all right, so if I'm trying to build nature, if I'm trying to build an atom called helium, this is how I would begin. 2 protons, then with 2 neutrons, and then set them in kind of a checkerboard pattern. Now, that's the center of the nucleus. On the outer edges, orbiting around, kind of like a miniature planetary system here. And so if you can imagine the sun at the center and the earth going around, I have then the third piece of this puzzle, which are the electrons. And of course, they're on the far outside. So you can imagine from history, these are the tiny subatomic particles that were discovered first. They're the ones that if you were taking something apart, kind of like these atom smashers, if you wanted to know what is in a car, but you don't have a wrench or anything to take it apart, you might just take 2 cars and slam them together and see what flies out. And so you can imagine if you take 2 cars and slam them together, kind of the first thing you're going to discover is they have a bumper. The bumper is usually what tears off first and comes flying out. And so sure enough, in the early bits of the scientific discovery of these what we call these atom smashers is we just smashed two atoms together, and the first thing that came out were these electrons. Now, we knew they had a charge, and so I'll just point out here that they come into play also when we talk about charge. They have the opposite of the proton. They're the negative, and so we talk about electricity and magnetism, and Benjamin Franklin will say that he's the one who then decided to label these things on the outside, although he didn't even know they were on the outside. He didn't know that much. But he knew there were these two types, and so he called one of them a negative and the other one positive. And it was later on we discovered that the negative goes with the electron and the positive goes with the proton, and the electrons are kind of on the outside orbiting around, kind of like the bumper on your car, and the positive, the protons, are the inside piece, kind of like the passenger compartment. So this would be more like, well, what's in the inside of the car, like the car seat, or maybe even further inside, the transmission and stuff here. And it's really just those three things that really explain the nucleus. And that's probably good enough. I think that's where your author kind of stops. He does touch one step further, so I will also go one step further, because in recent decades, we have discovered then that the neutron as well as the proton is actually made out of little tiny things. And so we call these tiny things quarks. And as scientists begin to do more and more atom smashing, and so let me just say more about the atom smashing. Like I said, it's kind of a weird way to think of it, but it's all we have to work with as scientists. If you wanted to know what was in a car, the first thing you do is you would slam them together, and of course if you did that at a slow speed, I'll call 30, 40 miles an hour a slow speed, what you're going to do is you're going to see a bumper come out. And so you're going to just see the electrons. But if you want to go a little bit deeper, and you want to know what else is in the car, back in the nucleus, these protons and the neutrons, you got to get the car going a lot faster. And so we made our atom smashers more powerful and more powerful and more powerful. So when we smashed them harder, we saw these protons and these neutrons come out. That would be like maybe the seat come flying out. You go, hey, this car has a seat in it. Or, hey, this car has an engine in it. And the engine comes flying out. But you might even ask a deeper question. Does the engine have anything inside of it? And so now you build a bigger smasher. And so maybe you're smashing the cars at 80 miles an hour and you're seeing the engine come out. But that's not allowing you to see inside the engine. So now you got to get these cars to go maybe 150 miles an hour or maybe 200 miles an hour and slam them together. And when they start hitting at that great speed, the engines fly apart. And then all of a sudden you see a piston and a ring come flying out. And you go, hey, you know what's in the engine is a ring. And so that's where we are in our technology. And so in recent decades, we've been able to build these things big enough that we begin to see that, hey, the proton actually has parts inside of it. And these are called quarks. And it turns out that the proton and the neutron are actually made out of the same quarks. They're just different amounts. That is, there's 3 each. The proton has what we call an up and a down quark. So pretty boring names, but 2 ups and a down. Whereas the neutron has 2 down quarks and 1 up quark. And just as a side note, you're probably wondering, well, what about these quarks? What about these electrons? Are they made out of smaller things? And that's a great question. And that's what science is asking today. And so now we're building bigger and bigger atom smashers, and we're smashing those together to see, hey, are those made out of other things? And so the answer, at least at the moment, is no. We have no evidence that there are smaller things that make up the quarks. or make up the electrons. Now that may change as our atom smashers go faster and faster. Like I said, if you smash it hard enough and a piston comes out, you may say, oh, that's what it's made out of. But if you got it going faster, one of the rings on the piston may come off. And you'll say, oh, that piston is made out of other littler things. But I didn't see it till I got the cars going 500 miles an hour. So I had to make a bigger atom smasher for that. And so who knows, it may change. But here's what I want you to get out of this, is that I would say then every atom, okay, in that periodic table is made out of three things. Electrons, and then you can either say protons, neutrons, or you could say electrons, up and down quarks. But whether you want to say those three, or kind of what I'll call the classical three, which was really where we're going to focus our attention, because we're never going to quite get so small to need to worry about or think about the quarks, we're going to say that we're made out of three things. Electrons on the outside, protons and neutrons, which we'll call nucleons, on the inside. And so every atom looks like this. This is what I'm trying to get at. This is the general structure. A nucleus that has protons and neutrons and electrons on the outside. Now, I should have pointed out that I drew this picture with two electrons. So coming over here to my desk model, I will grab the red ones to represent the electrons. And so they are kind of orbiting around. And as we will learn later, they don't really like each other. That is, their like charges, they repel. So they'll get on opposite sides as they go around. And so I can't really show this with my blocks or even in that picture, although I can draw a line. You can imagine these kind of orbiting around. This is the mental picture I want you to have for the structure of the atom. What does every atom look like? And the reason I picked two is because nature prefers, doesn't have to happen this way, so I want to emphasize that. Nature would prefer to have an equal number of electrons, because they're negative, to match the equal number of protons. So given the fact that I have two protons, we like to say that most likely I will have two electrons. Don't have to. Remember, they're on the outside. So we could take them away or even add to it. But I want you to get, let me come back over here to the periodic table. Here's the beginning part of this chapter. Hopefully what you're getting out of this then is I could pick anything. Let's do 10. And so if I pick on 10, which again from the Latin SN, I would say that in the nucleus, I would have 50 protons. That's a lot of protons, so I'm not going to try to draw all those, but I think you get the idea. And then if I look down here, which says 118.7, let me just round it to the nearest one, 119. The total number of nucleons would be 119. So the number of neutrons would be subtracting the two. And so what does that make? 69? So I've got to have 69 neutrons and 50 protons in the center, in the nucleus. And then on the outside, I would have orbiting around it 50 electrons, or maybe a little less or a little more. Like I said, it doesn't have to be 50, but it likes to be 50. So if I'm going to draw or talk about what we'll call a neutral atom, let me draw it as 50. All right, so I hope this first part got across, that you see, and I'll say it again, this is the whole point. Do you see how all of these atoms are essentially the same? They're made out of three things: neutrons, protons, and electrons. It's just a different number of protons and a different number of neutrons and a different number of electrons that make them unique and individual. But they all have a nucleus with protons and neutrons in them. They all have electrons orbiting there. And so you can look at this periodic table and pick anything. I could pick nickel and do the same thing. I could pick copper and do the same thing. I could tell you why copper is different from nickel. In fact, again, coming over to the periodic table, I would say that copper is different from nickel right here because it's got one more proton. In fact, every one of these is different because of the different number of of protons. And so that's what makes the atom unique. Well, let's keep talking. Because let me ask you this. What would happen if? What if one electron was missing? Okay, so let me come over to here and take this red block away. So I take this red block away. What do I have now? Do I still have helium? And the answer is yes. Now, let me say it again. What makes helium helium is the number of protons. So do I still have 2 protons? Absolutely. So as long as I have 2 protons, I have helium. The other things, the number of electrons and the number of neutrons, as you'll see, is not what determines the element. It's the number of protons. So if you take this away, I still have helium. Now, we like to write it this way, though. We like to say you have an ion. And so we have helium, but it's not a neutral atom. And we symbolize that in words by saying we have an ion. It has a charge to it. In other words, we aren't balanced with an equal number of positives and negatives. And so remember, the protons have positives, the electrons have negatives. So when I had 2 protons and 2 electrons, I had just what we call the atom. It's neutral. But as soon as I take away that electron, I now have 1 more positive than negative. I have 2 positives and 1 negative. So we like to represent this with a little plus, and then we like to use the word, I have a helium ion. What if I took away the other electron? What do I have now? Let me say it again. I still have 2 protons. So I still have helium. And since it doesn't have a neutral charge, I'm going to call it an ion. And so I have a helium ion. Of course, in this case, we would call it a +2. And that's how we would distinguish between that. And so we can tell how many electrons are present. In fact, this could even happen. It's not very common, but under rare circumstances, a wandering electron gets caught up. No, I don't want to put it in the nucleus. I wish I could put it far away and up here and it would stay. But I'll leave it there. But it would be in that atom. And what do I have then? And I would say the same thing, that I know I have helium because how many protons do I have? 2 still. But again, I don't have a neutral one. In fact, I got 1 more negative. So I would represent it with a negative up here. And all of these would be referred to as the ions. Now, let me go back to the neutral one here and ask this question. So back to the neutral. What if I took away one of the neutrons? What do I have? Now, let me say it again. What determines it as helium is the number of protons. Do I still have 2 protons? Yeah. So I would say I still have helium. I would also say it's neutral, right? I've got 2 protons and 2 electrons. But there is something different about this. It's not what I would call the normal one. See, the normal ones are the ones that are listed on that periodic table. When I see that number 4 up there, that number 4 tells me there's 4 nucleons. That means 2 protons and 2 neutrons. What I have now is 2 protons and 1 neutron. So what do I call that? Well, we like to call that then helium 3. The 3 is because we've got 3 nucleons. And so we'll put a little 3 up there. It means over here I could have labeled this as helium 4. But a lot of times we don't even bother to put the common one. So the one that's in there is just kind of implied. So if I put helium, I know it's helium 4. I don't have to say it's helium 4. But to make sure that I'm talking about a helium-3, I need to put a 3. Because if I just put helium, that implies that we're talking about the normal helium. All right? Let me ask you this. What if it's the other way around? And so let me put this neutron back. Okay. And let me put another neutron. And so I have a little extra, if you will. I guess I would label this as helium-5. Because I got 5 nucleons in there. I know I have to have 2 protons because it's helium. And so to have 5 means I must have, to have 5 nucleons means I must have 3 neutrons. And of course, if I'm going to say it's neutral, I need to have the 2 electrons. Well, I'll stop there because of time and I want to keep going there. But this are called our isotopes. This also explains a very important piece here. If I come over here and remember I said, and maybe I should point to it, that this number right here, this 4.003, the reason it's not exactly 4 is what the scientists do to label that is they take, and for lack of better word, I'll just say a spoonful of helium. I guess the truth is it's probably a test tube full of helium. And then they go ahead and see what the number of nucleons is on average. Did you catch that? So if I come back over to here, and I'll put some numbers on the board. Let's say my first helium atom in my test tube has 4 nucleons. My second one has 4 nucleons. My third has 4 nucleons. My fourth one has 5 nucleons. My next one has 3 nucleons. My next one has 5 nucleons.